Hello and welcome to my third and final watershed presentation on the Hughes River. In this PowerPoint I'll be doing some remote assessments of bank and general stream qualities to give them a Roskin classification and a bank erosion hazard index rating. This and the following few slides will be photographs from biological and habitat assessments by the West Virginia Department of Environmental Protection at the Hughes River Mile Point 1.5. This is a view facing upstream, and as you can see the channel's pretty wide and there's some decent developed canopy on the banks. This is a view of the Hughes River facing downstream. Notice on the right descending bank the gravel bar formation. In this picture, notice the composition of the bar, sandy and gravelly, as well as the angle of the banks. Because I wasn't able to visit the site in person, I made this sketch of the channel based on the above pictures, and from there I was able to measure the angles of the bank with a protractor on the image. As you can see, the left descending bank is about 42 degrees and the right descending bank is about 50 degrees. Let's move right into the stream class determination. In the bank full measurements, I was lucky enough to find a form from 2008 that the Department of Environmental Protection filled out in addition to the normal habitat assessment form that analyzed things like the bank full width and depth. So, in order to calculate this measurement, I was able to actually use measured data from about 10 years ago. So the width was 48.8 meters and the bank full depth is 1.55 meters. So the width to depth ratio is 31.5. For sinuosity, I used Google Maps measure function, which is really handy and it lets you plot points along a course and it ends up telling you the length. So I was able to plot points along the stream and came out for the stream length of 14.65 miles. And the valley length itself I plotted about down the middle of the valley using the satellite and terrain maps and came out with 10.08 miles for the valley length. So the ratio of those together is 1.45. So to calculate the entrenchment ratio, I used the bank full width that the Department of Environmental Protection determined in 2008, and I estimated a flood-prone width just based on what the pictures looked like. So the entrenchment ratio came out as entrenched at 1.12. And the bank full height to actual bank height, once again I had to estimate the actual bank height from the photos and came out to about 15 feet. Based on one photo that had one of my coworkers standing in it. And I converted the meters of the bank full height to 5.085 feet, and the ratio there came out to 2.94. So, for riparian vegetation information, I just estimated these values from the photos above. As you could see in the photos, the vegetation was pretty varied and extensive, with a developed canopy, some minimal understory, but also a lot of ground cover in long grasses towards the actual water line. So I estimated the total area vegetated on the banks as 80% on the left and 85% on the right, and estimated the total height with tree roots as 70% on the left and 75% on the right. This was not actually in the form that I had to fill out to determine the stream type. However, I determined it was necessary to actually figure out the type. So, I found the highest elevation in the watershed was I found a town near the confluence of the North Fork and the South Fork, and I believe it was called Petroleum, and the elevation there, according to the USGS, was 699 feet. So I found in the TMDL report the lowest elevation in the watershed at the mouth of the river was 582 feet, so it was an elevation change of 117 feet. So I divided that by the stream length from Google Maps. I converted the miles to feet and came out with 77,352 feet, and the slope came out to 0.0015. And I also had to determine a dominant substrate type to help with the subclass of the Roskin stream classification. And I included in the next slide a few substrate profiles that the Department of Environmental Protection did in several years. And you can see that, I guess based on flood activity and sediment movement, the dominant substrate actually changed a little bit, but overall in most of the years I looked at, gravel, whether fine or coarse, was the primary sediment, but there was also a lot of sand as the secondary most common sediment particle. So, as you can see, sand was a lot more common a particle in the 2015 survey, but most of the dominant substrate type in 2017 was coarse or fine gravel, with sand often coming up second. So, according to this handy-dandy flowchart from the Federal Interagency Stream Restoration Working Group, I was able to determine from all the numbers I came up with above that the Hughes River main stem is a class F4. F based on the calculated characteristics and 4 based on the sediment type. Alright, here are some characteristics of class F streams. They tend to be entrenched and meandering, and have high width to depth ratios. Their layout tends to mean they have a high capacity to deal with sediment, whether they're supplying or storing it. The storing comes from bar formation, which you could see in several of the photographs above, and they tend to have a decent capacity for bank erosion. And this is from the fact that these streams tend to be in a stage where they're trying to reestablish their floodplain, which means their channel width is usually expanding into the valley. This image will let you compare Class F streams to other stream classifications. This image gives you a more detailed view of the way channels get entrenched in Class F streams compared to the others. As you can see, the banks are pretty high and entrenched. This chart is similar to the previous charts I've showed, however it actually factors in the appearance of the different substrates and shows what all the other channels look like with different substrates and different classifications, so it's kind of neat. Alright, now on to the Bank Erosion Hazard Index. So, most of these values I took from DEP data or my own estimations from photographs. So, the bank height above I estimated about 15 feet, and this scored high, 10 out of 10 for the hazard index. The root depth I estimated in the 50 to 89% region, so that scored a 3 with a low hazard. Root density also scored a 3. Surface protection, since there was heavy vegetation, I estimated in the very low category, so it got a 1 out of 10. Bank angle, I averaged the two angles I came up with from my sketch and came up with 46 degrees, which was low. Not very low, but still pretty decent. And because the soil was gravelly and sandy, I added 5 points to the score and didn't have to adjust it for stratification because I couldn't tell that there was any. So it scored a moderate overall 25. And this seems consistent with the assessment that the DEP came up with in 2008. This is the actual 2008 form that the Department of Environmental Protection had on file for this stream's bank erodibility potential assessment. So, as I did in my own assessment, they scored low, as in a low hazard, for the bank angle and the root density, as well as the lack of stratification. The Factors that were concerning, however, were the bank height and the sandy composition of the soil. So this overall, I would say, was a more moderate score as well. And these were my references. I have to give a lot of credit to the West Virginia Department of Environmental Protection, not only for the experience I had working on the TMDL sampling for this stream and its watershed, but also for the ability to access old forms and photographs and other resources. I couldn't have done lots of this in a way that I was comfortable in accuracy without the input from their resources. I would like to thank you all for watching this video and hope you learned a little something or are inclined to go visit. It is an impacted watershed, but it's a very interesting agricultural area, so it's worth a visit if you're interested. Have a great day. Thanks.